Hi guys, welcome back to my channel. Let's become a bite better. Before we proceed, I request you to pause the video here and give a try by yourself to this question. The question for today is maximum number of nodes after connecting trees 1. So there exists two undirected trees with n and m nodes with distinct level of ranges 0 to n minus 1 and m minus 1 respectively. In example 1, the tree is given to us. I have just drawn it here. Okay. You are given a 2D integer edges 1 and edges 2 of length n minus 1, m minus 1 respectively, where edges 1 I, ai, bi indicates that there is an edge between nodes ai and bi in the first tree, and edges 2 I is equal to ui, vi indicates that there is an edge between nodes ui and vi in the second tree. You are also given an integer k. The question for today is maximum number of nodes after connecting trees 1. So these are the edges and this is an integer k. Node u is target to node v if number of edges on the path from u to v is less than or equal to k. That means node u, if v is 0, then u is a target to v if number of edges from path u to v is less than or equal to 2 in this case, because k is 2 here. So 1, 2, right? If v is 0, if we are at node 0, then 2 and 4 are target, right? If we are at node 0, then 2 and 3 are target, right? If we are at node 0, then 1 is also a target. If we are at, because for reaching the both, we have used only 2 hops, right? Either 2 or less than 2, right? So here, the first target, the first thing where we reach 2, 4, 2, 3 and 1, right? And note that node is always target to itself. So for 0 is a target to itself, so we can reach 0 by itself. So standing at 0, I can reach 5 nodes here, right? So here, the first return an array of n integers answers where answer I is the maximum possible number of the target to node I of the first tree if you have connected one node from the first tree to another node from the second tree. Okay, so if you have put a connection between these two trees, then maximum possible number of nodes you can reach. Then we have already calculated that we can reach 4 nodes from here and the node itself, that is 5. Now let us see. Here we can reach to, we have already calculated 1 node and 2 node, right? We can reach to standing at 0, 1 node and 2 node, right? Here we can reach standing at 0, 1 node and 2 nodes, right? So these were the 4 nodes that we can reach, and these are the new 4 nodes that we can reach. So we can reach 4 for 8 plus 1, 9 nodes, right? Standing at 0, the maximum node that I can reach is 9. We can reach to standing at 0, 1 node. So I have to get this path that where we can connect this so that I can get the maximum output. I could have connected this to 1 also, right? We will see the iteration right now. Now let us move ahead. Note that queries are independent from each other. That's why for every query you will have to remove the added edges before proceeding the next query. Okay, we will see that in dry run. Let me make some spaces. So I will be connecting to each node of 0 and right now I will try to look at this. So maximum element that I can get to by connecting 0 to 0 is k is 2. So in 2 hop we have to reach it. 1, 1, 2, 1, 2, 1, 2, 1, 2, and 1, 2, right? So if a person is standing at 0, the maximum reachable nodes from 0 after connecting the 0, 0 is 5 from the first one and 4 from the second one, right? So total is 9. Now let us say that we connected a path from 0 to 1. After connecting to 0 to 1, we can see that this person can hop in 2 go 1, 2, 1, 2. So reachable nodes are 4, 1 and 0 from second, right? This person can hop. Let us go and update here. This will be 5 plus 3. That will be 8. 3. Let us connect it to 2. And see that how many elements he can reach in 2 hops. So 1, 2, 1, 2, right? So in total he can reach 3 elements, right? Let us just consider that it is connected to 3. Now he can hop only 1, 2. So here 2 elements. Now it right. Now let us see how much he can hop from here. 1, 2, 1, 2, 1, 2, right? So he can hop these 4 elements, right? 5 plus 4, which is equal to 9. 5, and we can say that he can reach the maximum nodes he can reach in 2 hop is 1, 2. That's it, right? So 2 nodes he can reach. 5, 5 plus 2, 7, right? Now let us go to 6th node and see that how many elements that he can reach in 2 hops. 1, 2, right? Only 2 elements he can reach in 2 hops. And see that how many. 28 is 7, right? 28, 1, 2, that's it. So 2 elements he can reach. Right? So we will consider the path that will be maximum. So either we can connect 0 to 0 or we can connect 0 to 4. In both the cases, it provides the maximum result. The maximum of all this is 9. That's why we have updated our element here to 9. The output of first element is 9 here, right? The maximum of. Now let us go to the second index. Now let us see from here how many index he can reach. Standing at 1, he can reach 1, 2. So he can maximum reach 3 elements. Getting my point? In 2 hop, he can take 1 and 2. That's it. So what I am going to do, I am just going to copy this up. This would be 3. Let us put a different color here. Now, if you guys can analyze what we are doing here, from 1 we are connecting 0 and analyze. Now we'll say that he can hop 2 elements from itself. Now with 1 and 2, right? 1 and 2, right? 1 and 2, right? So he can hop 4 elements here, right? And that's what 4 is written here because we have already calculated it 1 and it once. So we don't need to calculate it again, right? Now let us try to connect this to 1. So in 2 hop, how many elements you can cover? 1 and 2, right? 1 and 2, right? So 3 elements it can cover. That's what is written here. So from this analogy, we can say that, right? Now let us, the maximum would be 7 here, right? We can see that once the maximum is calculated for the second task, there is no need to, calculate it again and again, right? Once the calculation is done, it is permanent for all. So we can connect this either to 0 or to 4. Calculate it now. If we do a same thing for like 2 and 0, so okay, standing at 2, how many can be reached? So 1, 2, 2 can be reached. 1, this can be reached. 1, this can be reached. So it can reach to all the 5 graphs standing at 2. So this would be 5 and this would be previously, it will look same as this graph, right? So 9 will be the maximum value. That's what we are getting here, right? How many can be reached? Similarly, standing at 3, we will get 1 hop, 2 hop, 1 hop, 2 hop. So we will get 4 nodes are covered here, right? So 4 plus 4, 8. Similarly, standing at 4 also will give us how many nodes we can cover in 2 hop. That is 1, 2 and 1, 2, right? So 4 nodes can be covered from here, right? Same, 4 plus 4, 8. 8 is the maximum. So we need to return this output, right? What we have observed here is that we need to calculate the maximum node reached from graph 2 once only, and then we can reuse it for every other node. Even we don't need to preserve the values of all, we just need to preserve the max value from here. From 0, the maximum we can reach is 4. From 1, maximum we can reach is 3. From 0, store this 4 with us, right? Because the maximum of the graph that we get is 4. We also don't need to know that which paths are connected, right? We just need to store 4. Store this 4 with us. Now we will iterate through all nodes in graph 1 and just add sum and then get our answers. Now let us see that what approach we will be taking. Now for level or order traversing, I will be taking the breadth first search. If I take breadth first search, what would be the maximum time complexity? And so how breadth first search will work? 0, level 0, at level 1 these would be covered, and at level 2 these would be covered, right? Till here we are considering, after that we will not consider these elements, right? Let us talk about the time complexity now. Let time complexity to create the adjacent matrices order of m plus n, and the time complexity to transverse through the second graph is order of m. There would be some relation between branches to k, right? Because how many number of branches will also affect, and how many hops it can take will also affect. There would be some relation. And what will be the time complexity of first graph? It will be order of n into max of n comma b to the power k, right? Let us say that this is t1, this is t2, this is t3, and total time complexity will be, let us say that the n plus m plus minimum of m comma b to the power k plus minimum of n into n minimum of n comma b to the power k, right? Let me just make it move it here, right? So time complexity will be this, and what will be the space complexity? Space complexity will be order of n plus m for adjacency list. Space complex visited set, this will be order of n, and for q it will be order of b to the power k. Revisited set, right? And the total space complexity will become, right? That's it. And let me provide it a different color to differentiate, right? So this is the whole case. Now let us move on to the coding part. First of all, we will calculate the number of nodes. So nodes will be number of edges plus 1, right? And nodes in 2 will be right. Then we will create the adjacency matrix, adjacency list. Since it is undirected, I am doing it for both the sides, right? Let us just create for. If you don't know how default dict works, then I have created a separate video for you. You can go and visit that. First of all, we will calculate the number of nodes. So nodes will be number of edges plus 1. Both the edges adjacency tests are met. Now what we have to do, we have to pre-compute the maximum value or the best value for both the edges, max for graph 2, right? So the max value for graph 2 will be for I in range n and 2, right? Let us say that we created BFS, that I'm going to create, right? And so let us move to this function for which node I am at currently with adjacency list 2 and the max depth, that will be k minus 1, because one hop has been consumed in creating the path, right? Because and we need to take the maximum of it, right? This is a very Pythonic way of writing it. And we need, once I get a max 2, what I have to do, I have to iterate same thing for max 1 also. Max graph 1, I have to do same thing for graph 1, but instead of creating max, I have to just return the whole thing instead of, okay, and I have to add here for all, I have to add max of G2, right? That's what we were doing. Return the whole thing instead of adjacency list will be 1 and k will be k, because no k will be consumed in creation of the path. No, also we don't need to store it somewhere. We can just return it, right? Now let us calculate this self. This self will be start. This is the start of the node, that will be int. Also we don't need to, we have adjacency, that is list, at default dict, that is of dict type, right? And then we have max depth that will be of type int, and its return type would also be integer, right? We have adjacency, that now we have to create a visited set. Start. Then we have to create queue. Now we have to say count 0 and depth 0, right? Now we will return the count, right? So we return the count. Now we will create our while loop, that is the main BFS. So while q and depth is less than max depth, right? Both conditions should be there. Here we will increase our count to 1. Once I have seen a node, I will increase its count to 1. Now I will visit its neighbors. And I will also append this to my queue. Right? Once I reach here, I will say depth plus is equal to 1, because I need to go up to the max depth, right? After this, I will return the count. Let me run this code. Oh, I am sorry, I changed this, but not others. Oh, I am getting the wrong answer. Okay, I am saying depth is less than max depth. It must be equal. Let me run it. Yeah, now it's working. Let me try to submit it. And yeah, it works pretty well. So that's it for today, guys. See you in the next one. Till then, keep practicing. That's it for today. Meet you in the next video. Till then, keep practicing.